Okay, so I'm going to get started. The last few announcements for today's last lecture. Chapter 24, Sapling, is due at the final exam. The final is a week from today, Wednesday, 7:30 a.m. in Math 100. And then the exam review is going to be Sunday, 10:30 a.m. in Dwayne G130, not G1B30. We're upstairs from there. Okay, any questions about that? Okay. I'm looking at trying to get all the Sapling and blah, 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 packback grades posted in Canvas by hopefully the end of this week so you can see where you stand numerically. But yeah, if you notice anything looking wonky by like Friday evening, then let me know either by email or at the exam review. Okay. Any questions about that? Okay, cool. So I'm going to sort of be skipping around, or not around, but like sort of, yeah. Oh, sorry, what? Yes. I think this week there is packback and next week there is not. And then I'm actually working on getting a survey to send out to you guys about how you felt about it, because I'm getting some mixed messages about people's level of taking it seriously, which that's, yeah. Like I'm seeing those. I just like do not have the time this semester to like go in and moderate. So that's kind of on me for just, yeah, sorry guys. But I feel like it could have been applied a little bit more usefully, but that's kind of like I want to get a poll of how people feel about it. Okay. Okay. So, yeah, I guess to sum that up, packback this week, not next week. And there will be a poll too. Okay, so the last bit of this chapter, we got a few things left about carbohydrates in this chapter. Some of them are a little bit, guys, I guess some of them, I have reactions towards the end of this chapter that I'm thinking I'm not going to expect you to memorize any of the reagents or what they do, but I am going to sort of skip mostly ahead to the Fischer proof. So if this comes up on the exam, rather than expecting you to know the reagents, like I might say, you know, this mystery sugar was hit with these reagents, and I won't expect you to know what that does functional group-wise. I'll just say converts this to this, and then you can use that information to sort of solve like an unknown structure, kind of like we do in the last couple pages of the notes. So I'll cover the reactions now briefly, but you're not on the hook for knowing sort of what they do, I guess, in other words. Okay, before we get to that though, I did want to talk a little bit about glycosides and polysaccharides. Okay, so we've been doing hemiacetal formation. So you can take, you know, whatever sugar and turn it into maybe say something like this if you cyclize 1, 2, 3, 4, 5, 6 hexose. All right, so we've been looking at this. This is shown specifically without stereochemistry. But remember that the carbonyl, in this case an aldehyde on the parent chain, that CO double bond is going to end up becoming the only carbon in the molecule that has 2 bonds to oxygen. So that's our hemiacetal. We can't really make a full acetal out of this molecule by itself as it currently exists, just because to do that we'd need to bring in another ROH part of the molecule, and it turns out just sterically and bond angle wise it's not really feasible to have this thing cyclize around and bring in the other ROH group that it would need to make the full acetal. But if we bring in a different separate ROH molecule, we can totally get the full acetal going there. And again, the mechanism is going to be pretty much exactly what we saw for just the regular hemiacetal to acetal formation in chapter 19. So if that's not ringing a bell, this might be a good time to go back and sort of review that stuff. If you guys remember hemiacetal, we could form with either acid or base catalyst. For the acetal, we actually, during the mechanism, have to turn this into a leaving group, and so it has to be an acid to make this happen. So this part actually does need to be acid catalyzed. Okay. So that's without stereochemistry. With stereochemistry, I'm not going to draw the whole thing. I think in the notes, like, I have the full structure drawn out, but I'm not going to emphasize stereochem. But if you did a Hayworth projection of it, you could show this as either the OR form is up or the OR form is down. So just like with the regular hemiacetal, like cyclic form, whether it's the 6-membered or the 5-membered ring, you can have alpha and beta forms of this. Have I given you enough information to tell which of these is the alpha and which is the beta form right now? Correct, I have not, because we need to know what the stereochemistry is like around here in the molecule at the lowest stereo center, and I haven't told you that. So one of these is going to be alpha, one's beta, but we don't know which one is which. Okay. So we can do this with a separate molecule of ROH. But what's most useful and interesting is instead of just a simple alcohol like, say, ethanol or methanol, we know that another carbohydrate molecule also technically counts as an ROH because it's got a bunch of OH groups on it. So what if we use another carbohydrate molecule as our R group? So, and I have these drawn out in chair form in the notes. I might stick with something a little bit simpler, but we could have, say we're doing this type of linkage, rather than going to an R group, we could have that be part of another carbohydrate molecule. So we're pretty much using one of the OH groups around this ring, and we have a lot of choices to which because there's OH groups all over this thing. I'll just start drawing some examples on. But we could pick any one of the OH groups around this ring and use that as our alcohol molecule and cyclize onto this by forming the acetal. So this is kind of how we link carbohydrates together into polysaccharides, or I guess disaccharides in this case, but you can keep going. And so forth. And again, you can link things together with either alpha or beta linkages or some organized pattern between those. There's so many different OH groups, and each one of them could be linked to the previous ring, alpha or beta. So we have a ton of different possibilities here. So this is what starch and cellulose and what's another one? Oh, chitin are all sort of long chains of carbohydrates linked together in different ways. They might not be all the same basic carbohydrate, and they're linked together in different ways. Like some are alpha, some are beta. And that actually affects whether the enzymes in your body are capable of breaking it down into small, like monosaccharides. As kind of a side note, that's why starch, if you like bite on a cracker and then let it sit in your mouth for a long time, it's going to eventually start tasting kind of sweet. And that's because the starch, which is this long chain of sugars, is going to get broken down by enzymes into individual sugar molecules. You can do that for, I want to say starch is all what turns out to be beta linkages, and cellulose is all alpha linkages, and I might be backwards on that. But you can break down one of those linkages, but not the other, which is why if you eat some cellulose, I guess like paper or something, it's not going to start tasting sweet at any point because you just can't break it down the way that animals that can digest cellulose can. And even then, it's not actually the animals themselves doing it. It's the gut flora that they have that's actually capable of breaking down cellulose. Okay, so basically ton of variations, ton of options in how to put these together. We're not going to go super in depth, but biochem will probably introduce you to a lot more ways that these things can go together. Okay, so questions about that? Okay, yeah.
Did you pick certain carbons to link together on purpose, or does it matter?
No, it could be like anyone around the ring depending on exactly which particular structure it is. And yeah, the chemistry on getting these things to go together is very complicated. Like if we're trying to do it in the lab, we can use protecting groups pretty heavily. Or if you happen to be an enzyme and can just choose exactly which part of which molecule reacts, then it's a lot easier. So, yep. Okay. So that's just kind of an overview. We're not getting too much into that. Okay, what we are skipping ahead to is looking at a couple of reactions that we can do on carbohydrates. So first of all, oxidation and reduction. Actually, I'm just going to lump these together. So reactions of carbohydrates, because I'm going to skip most of this section except for one reaction. So I have this whole table here. And really, we only need to know about one section of it. And I will also give you the results of this sort of if you need to know them for the exam. But assuming we're starting with an aldose, an aldehyde-ended sugar, whatever OH group's on there, it turns out we can kind of selectively oxidize what happens to both ends. So right now we have an aldehyde up top and an OH group on bottom, a primary alcohol. If we hit this thing with dilute HNO3, we're actually going to turn both ends to carboxylic acids. Okay. So this turns out to be kind of useful for something that we're going to look at for most of the rest of the class, the Fischer Proof, because what this does is turn both ends into the same functional group, which means that we can actually use that to determine now how symmetrical is our molecule, because if both ends are the same and all the stereocenters in the molecule are the same, we actually turn this into something that should be optically inactive if all the stereocenters are symmetrical. Okay, so that's actually super heavily exploited in the Fischer Proof, which we'll see in a second here how to use that. Okay, there's a bunch of other options and combinations we can go for, like turning this into an acid and leaving this in alcohol, or reducing them both to primary alcohols. But really, this is kind of the only one that we're actually going to use. So it's the only one that's going to come up for us. Okay, questions about that? Okay, cool. So the other reaction that we're going to use for the Fischer Proof is the Kiliani-Fischer synthesis. Okay, so if you guys remember, we saw this one show up real briefly in chapter 19, didn't really spend much time on it, but if you have some source of cyanide ion and some kind of protic thing, and you have a carbonyl. This can come in, attack the base of the carbonyl, kick that up. And you end up with an extra carbon, which is now a C triple bond N group there. Okay, so this is pretty much the same as like any other base catalyzed kind of addition to carbonyls from chapter 19. So any questions about that before we start applying it to carbohydrates, where things get complicated? Okay, cool. So now let's bring stereochemistry into it. I'm just going to show like the top end of a molecule without drawing the rest in. But if we have an aldehyde here, and we attack it with C triple bond N, we're going to get a new stereocenter here. And we could get that on the left side or the right side. So we're turning this OH group into, or turning the carbonyl into a new OH group. We're going to put the most oxidized carbon at the top here. And the new OH group could point to the left or to the right, and we don't really have much control over where it goes. Okay, so we make a cyano group here, and then we didn't really cover this next step as its own specific reaction, but we'll do it here. It turns out you can sort of, actually I guess we did sort of, so H2 and a poisoned catalyst like Lindlar, so palladium and barium sulfate is the specific version they use for this, but just think of this as like palladium with some stuff in it that only lets you reduce down one step, so we get the C double bond N, and then that if you hydrolyze it, H3O plus, you get the carbonyl out of it. But again, the OH group that you formed during the reaction is still around, and it could be pointing either way. Okay, so ultimately what we're doing here, okay, so NaCN and H2O is the version that we're going to see here, just CN minus and then some kind of protic source. Okay, so ultimately what we're using this to do is extend the chain upwards by one carbon, and the new stereocenter we add by doing that is kind of random which side it's going to be on. So we're going to get a mixture of like new stereocenter on the left, new stereocenter on the right. Okay, so these are both epimers of each other. They're only varied at the top stereocenter. Okay, so questions about that? Okay, cool. So those are the only two reactions that we need to know to see how cool the Fischer proof is. Okay, so this is how they figured out the structure of what's probably the most prevalent and useful sugar for humans, glucose, or the most prevalent monosaccharide anyway. Okay, so this is long before any sort of NMR or much in the way of spectroscopy for organic molecules. So this is all just sort of a big logic puzzle using what we know about symmetry and optical activity and looking at sort of how different changes on the molecule affect its optical activity. So because we can't tell like ultimately R or S for any of these stereocenters, Fischer pretty much just had to pick one at random and guess, and then determine everything else relative to that, so like on the same side versus the opposite side of the chain. So he just picked the lowest stereocenter and decided to put that on the right. So we're just going to guess that it's on right. And it wasn't until like most of a century later, I don't remember what year this was actually published originally, but eventually people were able to figure out through like X-ray spectroscopy of crystals and figuring out exactly how the things are put together that he did actually pick the right outcome for this. Like it was pretty much a coin flip and he guessed it right. Okay, so in other words, we're assuming that glucose is a D sugar, which it turns out to be. Okay, so from there, we're going to determine the other stereocenters based on a few things that we know when we do reactions on this molecule, glucose. Okay. So here's what we know. And I'm going to be using plus and minuses in parentheses here. If you guys remember, we haven't really seen too much of these lately, but this is just saying what direction it rotates light. So like clockwise versus counterclockwise. I'm going to be putting up the names of some sugars here, and you don't know what those structures are, and neither did Fischer at the time. He just knows I have this sugar called arabinose with these physical properties. It rotates light counterclockwise. When I do some stuff to it, then I get some other things out of it, and we can figure out what those are if we put sort of all the information together that we have. So minus arabinose is converted to a mixture of plus glucose and plus mannose by Kiliani-Fischer synthesis. Okay, so, oh, I'm sorry, I left one thing out of here, and that is, I should say this is plus glucose that we're looking at. Okay. So plus glucose was the most sort of dominant form that's sort of the natural enantiomer of it. Okay, so we know nothing about the structure of pretty much any of these, but we are guessing that oh, I guess we do know the formula of how many carbons they have. So we know that minus arabinose is a pentose. It's got 5 carbons in its formula. And we know that these two are both hexoses. Okay. So minus arabinose, don't know what's going on in the middle. We do Kiliani-Fischer to it, and we get a couple of hexoses. So we don't know any of these for sure, but we are assuming that all of them are the D form because we're just guessing that the bottom thing is on the right. So that's not going to get changed by the Kiliani-Fischer synthesis. The only difference between these is that one's got the OH on the left and one's got the OH on the right. Okay, so that's minus arabinose. And then these are plus glucose and plus mannose. We don't know which is which. Okay, so that's all we got so far. Questions about how I'm sort of figuring this out so far? All right, cool. All right, so then he did a few more tests, and he also found out that minus arabinose is optically active when you react it with HNO3. Okay, so if we start with minus arabinose here, okay, with HNO3, that's going to turn both ends into carboxylic acids. And we know that nothing's going to change at this lowest stereocenter, the one we guessed on. We do know that this is optically active, so there is not a plane of symmetry here, in other words. So what does that tell me about my upper stereocenter here? Which way is the OH pointing off this guy? Yep, yeah, I'm seeing people point to the left. It's got to be on the left, because if it were on the right, then this would be symmetrical and it would be optically inactive. So top OH must be on the left here for this guy. Okay, so that means that we can go back and plug in this stereocenter on glucose and mannose. And that means that those two guys look like all right, so we already knew this much from before. One's got OH on the right, one's got OH on the left. And so now we know I guess the third one up from the bottom is how you could look at it. Like this one here is OH, which means this one here is OH, which means this one here has to be OH on the left. Okay, any questions about how I'm making that conclusion? Okay, cool. Okay, so, yeah. Oh, sorry, where? Oh,
How do you know the second one again? Is it because it's like 3 at the top and 4?
Yeah, and so like this one is the new one that got formed when you did Kiliani-Fischer synthesis, and so we're sort of looking at like the bottom one and then up a couple, and this one is the one we just figured out based on the HNO3 thing. Yep. Okay. Any other questions on that one so far? Okay, cool. All right, so a little bit more time in the lab, and he found out that both glucose and mannose form optically active products after being oxidized with HNO3. So, isn't it? So we know that they both have to have the same unknown stereocenter here for both of them. We still don't know which is which, but I think I have room to split this down the middle here. So if we put so if the unknown stereocenter for both of them has OH on left, then if we oxidize both of these, okay, so we're hitting both of these with HNO3, we're oxidizing both ends, but the rest of the stereocenters should stay unchanged. So that's the same, that's the same, that's the same. And if we assume the unknown stereocenter has OH on the left here, we put that there, then we're also copying this down, so OH there, we're assuming this one is on the left, and OH there. Okay, so this one is optically inactive. It's symmetrical right down or right across the middle. While this one is optically active, it's got no such plane of symmetry. Okay, so if we assume the unknown stereocenter has OH on the left, then we should expect to see one inactive and one active product, which is not what we're actually seeing experimentally. So let's try assuming the unknown stereocenter has OH on the right. Okay. Okay, so again, we're copying everything down from these two up here, just I'm making an assumption about the unknown stereocenter. So OH, 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 OH versus OH, 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 OH. Okay, so both of these are optically active. There is no plane of symmetry here. And there's no plane of symmetry here. All right, so this assumption must have been correct. The unknown stereocenter has to have OH on the right. Okay, so you with me so far? Like, any questions about this? Okay,
Is the first inactive part for the MX center supposed to have the acid on the bottom as well?
Oops, yes it should. Good catch, thank you. Yeah, and yeah, it looks like I got the rest of them okay. Okay, cool. Okay, so other questions about this step? Okay, cool. So we've figured out what glucose and mannose look like. Problem is we still don't know which is which. So which is which? Okay. So the last bit of evidence that we needed turns out to be plus glucose forms the same. Oh. Okay. Sorry, I'm just realizing. Nope, okay. No, we're good. Okay. Okay, so I didn't cover the specific name of what the carbohydrate becomes when we oxidize it with HNO3, and so I'm sort of skipping around in the notes, but yeah, we don't need that to finish this up, it turns out. Okay, so plus glucose when reacted with HNO3 forms same product as a different carbohydrate plus glucose and so we also don't know what plus glucose looks like, but we're assuming that whatever's going on in the middle here if we take glucose and flip it upside down, then we're going to get the same product as glucose. So glucose after HNO3 is just drawn upside down from glucose after HNO3. Okay, so we still don't know anything about the middle of these, but let's see if we play around with the structures that we figured out so far, and maybe we can pin down which one is going to be which. Okay, so let's redraw my two here that I've got. Okay, so if I flip one of these upside down, then I imagine that I'm sort of reversing the HNO3 process. That's not something I can chemically do that easily, but what I want to do is sort of look at how might it have looked before I oxidized it if it were upside down. Okay, so let's see. Okay, so first I'm going to flip it, and then I'm going to sort of assume like whatever this is the oxidized form of glucose maybe. So before HNO3, this would have been okay. The problem is that this is the same. Yep, question. Yeah. Mm-hmm.
What did you flip?
So, so I'm taking this whole thing, I'm turning it upside down, kind of like I showed up here. Yeah, so, okay, so, okay, so this is kind of the hardest part to see, I guess. So, yeah, you're right. Okay, sorry, I'm doing this like a little bit formatted differently from the notes because I think I was trying to make it less confusing, and I don't think that panned out, actually. Okay. So, okay. So if I do flip this upside down, okay, so these ones rotate up and around. This one comes down to here. Okay, there we go. All right. Yep, sorry about that. Okay. Here we are. Okay. Yep. So this one rotates up to here. This one rotates up to here. Yeah, so I'm spinning the whole thing upside down. Yeah. And this one rotates around to here. And this one rotates around to here. So I'm basically taking this whole thing, flipping it 180. I was just drawing it wrong. Sorry about that. Okay. Okay, so we should have, instead of right, right, left, right moving up, we should have left, left, right, left moving down, if that makes sense. Okay. Whew. All right, so we do that to this molecule. We flip it upside down, and then we sort of reverse the oxidation process, or pretend that we're, this is like oxidized glucose. And so here's what glucose must have looked like. And so then the question is this the same as what we have up there? Nope, it's a different molecule. Okay. So that's telling us that we are getting a different molecule. Or in other words, if we take glucose, which is a different carbohydrate, and oxidize it at both ends, we're getting the same product as oxidized glucose, just it started out at a different place. So okay, so both of them oxidize to the same product. If we try doing that over here, okay, so again, we're rotating everything around 180. These rotate up to here. So, and then if we reverse the oxidation process on that, then we're actually getting the same molecule that we had when we started out. So because this one turns out to be rotationally symmetrical, like if you flip it upside down, you end up with the same thing, that tells you that this one is not going to make a different different isomer. Okay, so in other words, this one is mannose. Okay, so we figured out what all the stereocenters in glucose and mannose are, and then finally, we've figured it out that which one is which is just based on how symmetrical they are before they oxidize. Okay, so that last step, sorry, I kind of botched that a little bit. Hopefully I didn't confuse anyone too much. It may be a little bit easier to follow along in the type notes as they originally were before I decided to go off script a little bit. But there's a couple questions like this in the sapling where they sort of give you some info and ask you to figure out the structure from scratch. Okay, so that's the last bit of lecture information. Thank you for a great semester, you guys. You've been awesome. And okay. And those of you who can make it, I'll see you at the exam review on Sunday. If not, I'll see you on Tuesday at the final, or if you want to drop by my office with questions. Hi.
Can I just request that you're extra careful to move the camera near 11 o'clock?